Chapter 7, Section 1, Question 1. You're going to have a mixture of a whole bunch of different types of problems, but you're going to have to evaluate each radical expression if it is a real number. Are they all real numbers? Of course not. Is it often going to be a real number? Yes, it is. So, back in Chapter 1, we prepared you for this question with the square root of 169, or possibly in previous math classes, in which case that answer is 13. This answer is negative 13. Ooh. Now, back in Chapter 1, we gave you the cube root of 0.008. Now we're giving you the cube root of negative 0.008. So the cube root of 0.008 was 0.2. Now it's negative 0.2. Now, why is this? This is because if you think about the work for this, it would be 13 times 13. If you have a pair on the inside of a square root, they will come outside once. If you have a cube root, you will actually need to have 3 of the same things, which are negative 0.2, negative 0.2, and negative 0.2. Since we have 3 of the same things, they will come outside once. That is how we get our answers. But wait, there's more. Here, what 2 numbers, both the same, will multiply to give you a negative? If they were both positive, a positive times a positive is a positive. If they were both negative, a negative times a negative is a positive. What 2 numbers for a square root could give you a negative? It can't. So what we write is we write not a real number. As before, do not write not a real hashtag. Do not write NARN, N-A-R-N. That means not a real number, because I will not take that for full credit. So I expect you to write not a real number, because with your English classes, if you are turning in something and it is your final product, you should not have all those abbreviations in it. So I do not expect abbreviations here. Now, big question. Why would this be not a real number? It's because you couldn't have 2 things, because this is a square root, you couldn't have 2 things that multiply to give you a negative, but you could have 3 things that multiply to give you a negative. Follow up. How many not a real number problems can you find? Go take a look in your textbook. There are a lot of those problems that are not a real number because they want you to get practice on what makes it not a real number. Quick tip. The rule for not a real number. All of these problems here are not a real number. Why? If the index is even, what is an index number? An index number is the little number here in the corner. In this case, a square root has an invisible index number of 2. Some students choose to write that in because it reminds them that it's not a 0 or a 1 just because you can't see it. It's a square root. If you think about it, x squared has a 2 up there. A square root has an invisible 2 up there. So, if the index number is even, 2, 4, 6, 8, 10, 12, etc., and the radicand, what is a radicand? That is this thingy on the inside. If the radicand is negative, then I write not a real number. This is in Chapter 7, Section 1 only, so later on we're going to have different answers. Don't worry, I'll tell you when that happens. Chapter 7, Section 1, Question 2. Aha, we are introducing you to the concept of even, even, odd. I'll tell you that even, odd is a thing. And originally, when I was teaching, students said, why do we have even, odds? And I said, oh, we're not grading on that this year. And they said, why are there even, odds? Or actually, they said, why are there absolute values on your answer? And the secret answer was, I had no idea. So I eventually went through about 10 different math books on how they taught it, and I found that not a lot of them taught it well at all. So I really looked at the question and the answers until I figured out the pattern of even, odd. So what's going to happen is when you're simplifying a square and a square root, they're going to cancel because they're opposites of each other. If you look at your calculator, you have an x squared button, and above it, you have a square root button. They're opposites of each other, and this is fairly common because those people who program their calculator and designed it. They actually thought about this. These will cancel and leave you with 2x plus 3. But because of the rule of even, even, odd, there is an invisible index number here of 2. We have the exponent here, which is 2, and we have an invisible exponent here of 1. And what that means is we need to put absolute values on that answer. Some students say, well, if this is invisible, do I need to have a parentheses along with the absolute value? No, you don't. However, the reason that I'm going to tell you to put those parentheses there is for safety, because by the time we get to the end of this chapter, which is one of the longest chapters that we have to cover, it has 7 sections, you will forget that this is the only time that we put an absolute value around the entire binomial. So, I would suggest that you do that. Otherwise, what's going to happen is you're going to end up putting an absolute value just around the x, and it's going to be wrong. So, I need to see that this step here, with the square and the square root canceling, and this step here with the absolute values. Now look at that. Some people look at that and say, oh my gosh, I need to snowflake, I need to diamond box, I need to guess and check. But this is a perfect square trinomial. If you need to review that, go back to chapter 5, section 6. All right. If you look at chapter 5, section 6, we only need to look at these 3 things here. The first term, the first sign, and the last term. And that will tell us how it factors. 25 will break up as 5. X squared will break up as x. The symbol is a minus. And 9 breaks up as 3 times 3. That is a perfect square trinomial. In chapter 5, section 6, I told you that if you wrote it as 5x minus 3 times 5x minus 3, back in chapter 5 and chapter 6 that was okay, but by the time we got to chapter 7 and we're here, you have to write it like this because a square and a square root, that's what cancels. That's why I had you guys writing it like this. Some of you have been writing it that way since chapter 5. Some of you wanted to wait until now. Now is the time. I want to see it looking like this. The square and the square root cancel. If you can do that in your head, great. If you need to cancel them out, great. We have 5x minus 3, and because of the even, even, odd, the invisible 2, the 2 there, and the invisible 1 there, we need to put absolute values. What if I forget? If you forget, please read the instructions. Use absolute value to simplify. If you don't have an absolute value, it's wrong. You may need to factor first. You may need to factor first. On your homework, you're going to have to factor first because we're not going to give you something cute like that. So, hey, almost always you will have to take this, factor it first, and then write the absolute values. It's going to ask you for 2 steps. Step 1, step 2. Please make sure that you have this with the parentheses and then the squared there, because otherwise, possibly taking out points. I don't want to take out points. Chapter 7, section 1, question 3. My gosh, we're going over yet more even, even odds. All right. If you look at this, we are going to have to use absolute value to simplify. There will be even, even odds there. You may need to factor first. We don't really need to factor a whole lot first, but you might actually need to. If you look at 625, we want to see how it breaks up. If you know that it breaks up beautifully into 2 exact same numbers, great. But let's say you didn't. Let's say you said, hey, it ends in 5, so I can take out a 5, and that leaves me with 125. Keep bringing this 5 down because a lot of students will lose terms or they will repeat terms because they don't know about which line is the last line. So I try and make it so that every line is equal to the line above it or below it. I can take out a 5 and I have a 25. Keep bringing these down so that each line is equal to the line above it or below it. Same as in chapter 1, same as in all the other chapters since then. Hey, look. 625 is equal to 5 times 5 times 5 times 5. If you remember back to chapter 7, section 1, question 1, with a square root, I need 2 of the exact same things. I have 2 of the exact same things. But wait, there's more. I have another two of the exact same things. What do I do with that? Well, when I have a pair, it comes outside once, and when I have a pair, it comes outside once. And some people incorrectly think that that is 55. But if we look here, these are all being multiplied, which means these are also being multiplied. It's going to be 25. Now, we're going to look for pairs. I could write out 18 A's, but let's not. All right, I want to know how many pairs are in 18. Let's put that invisible 2 back here. 18 divided by 2, that will tell me how many pairs. 18 divided by 2 gives me 9. Ooh, let's check for even, even, odd. It has to be a variable. It has to be a variable that came out all the way. So none inside. And then it has to be even, even, odd. Many students do not understand even, even, odd, and you'll be happy to know that we're actually taking that off of a lot of different sections. So what we're going to check for even, even, odd is the index number, the original exponent on the inside, and the ending exponent. Even, even, odd. That isn't even, even, odd. We put absolute values on that. 24 divided by 2. 24 divided by 2 is 12. That's how many pairs I'll have. B to the 12th power. Is that an even, even, even? We only care about an even, even, odd. So with an even, 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 we don't do anything to that, but we do have to simplify that 5 times 5 is 25. The absolute values only go around the A to the 9th power, and then the B to the 12th power does not have absolute values on it. Make sure that this goes around the A and the 9th power. Technically it's correct if you didn't have it like that, but that's not how anybody writes it. So keep the A to the 9th, the entire term, inside of that absolute value. Besides, I think you could actually get into some trouble if you didn't do that. All right. Now, let's say that you did know that 625 broke up into 25 times 25. You don't have to keep breaking it up because we have a pair, bam, it can come out immediately as a 25. You don't have to show the extra work. This shows you, hey, lots more work, but even if you don't know that 625 is 25 times 25, you can still find the answer. That is important. Also, notice that every single line still multiplies to equal 625. That is also important. So, over here, if you need to show the work, great. That is your answer though. Chapter 7, Section 1, Question 4. This question is a blast from the past. It is from Chapter 3, Section 2, Function Notation. We're going to use function notation again. Back in Chapter 3, Section 2, we often had you plug into a linear equation. We also had you plug into things that have x squared, which is called a quadratic equation. We had you plug into formulas that had those big honking lines on it that were called absolute value equations, and were shaped like these. But now, actually, back then also, we had you plugging into square roots. So, let's go over this. This is the formula, and what we're going to do is plug, work, and answer. The question goes on the left-hand side, and we're going to plug it in. 4 times 3 plus 13. Work and answer. The work that I want, if you want to do 2 steps of work, you can do 12 plus 13, but what I really want to see is, what is 12 plus 13? That is 25. And then, f of 3, the square root of 25 is 5. If you want to cut out one of these steps so that there are only plug, work, and answer, I need to see the plug, of course. I need to see this one, which is the final work right before the end, and then the answer. So if you feel like you can skip this step, I will let you skip this step. But for those of you who are wanting to show as much work as possible so you don't make accidental mistakes, this is how you do it. Now let's say that you want to look into the future. Tying together both chapter 3 and this chapter here, do you remember that f of x is equal to y? I hope you do, because the 121 students are having to deal with this. So if I have f of 3 equals 5, this is actually secretly the ordered pair 3, 5. This has nothing to do with what we are doing right now. All we want to see for this chapter in this section is, can you plug, work, and answer? Sometimes the work needs a little bit more steps than just one, but plug, work, and answer. If you're going to only have one line of work, this is the line I want to see. Chapter 7, Section 1, Question 5, Type 1 of 2. Remember back in Chapter 3 when we were having you make T-tables? Same thing. We're going to use T-tables. T-tables are wonderful because when you forget how to graph something, they should always work. Here we go. I'm first going to graph out the square root of x. Here's my T-table. Often, we use numbers like 0, -1, -2, +1, and +2. If I were to plug that in, I would get the square root of -2. If you remember from Chapter 7, Section 1, Question 1, that has an even index and a negative radicand. It won't work at this time. Then, if I do square root of -1, it has an even index and a negative radicand. It won't work. I'm just drawing a dash there to show that we're not going to be graphing that. It's not actually a negative sign. All right, then we're going to plug in, hey, what number times itself will give you 0? That is 0. What number times itself will give you 1? That is 1. What number times itself will multiply and give you 2? Nothing nice. It'll be something a little bit bigger than 1. But we're not going to graph that. What we're going to need to do is keep going. I want to get at least one more because this is a nonlinear equation. 2 points is not enough. Square root of 3. That's still bigger than 1, but it's not nice. The square root of 4. Square root of 4 comes out nicely as 2. These are the ordered pairs that I'm going to be graphing. I want 0, 0, 1, 1, and 4, 2. This will help me graph. Whee! All right, that is my square root graph. Now, it might look familiar to you. What it should look like is a parabola that has been flipped. But because of even, even, odd, this bottom part got absolute valued, so it came up like that. That's why it only goes this way. Also, if I still had the bottom on it, it would no longer be a function. And this is called function notation. You'll remember from Chapter 3 that we used f of x, but we can also use g of x, h of x, j of x, a whole bunch of different letters. In fact, later on, we'll change the f of x into things like m of a, p of z, things like that, because we can. All right, and they're variables. Now, let's think back to Chapter 3 also. When we were graphing out parabolas, we thought about 1 squared is 1, 2 squared is 4. We're doing it sideways now because it's going to the side, because this is actually going to be called an inverse of the square property, and we'll get more into inverses in Chapter 9. So if we count from our starting point, which is at 0, 0, 1 squared is 1, go back to the original, 1, 2, 2 squared is 4. If we wanted another one, we would go 1, 2, 3, 3 squared would be 9, the next point would be out here. You might even want to show where that is so you know where you're aiming at when you're drawing your graph. That is going to be the best. But wait, there's more. Here we have g of x is equal to negative x. So if I were to make a t-table for that, it would be very similar to the positive square root of x. This is just a negative square root of x. So if I have negative 2, negative 1, 0, 1, 2, negative square root of negative 2, I still have an even index and a negative in the radicand, so I don't graph it. Negative square root of negative 1, I have an even index and a negative inside of the radicand. I don't graph that. negative, square root of 0. The square root of 0 is 0. There is no negative 0, it's just going to be 0. Negative square root of 1 gives you negative 1. Negative square root of 2 does not come out nicely. And again, we're going to have to just keep going on until we find at least one more point to make sure that we can get that pattern going. And just like before, the square root of 4 is 2, that will make it negative 2. So now, by having the negative, we have these points. 0, 0, 1, negative 1, and 4, negative 2. And we can make our starting point here and go whee! Now be very careful. I have seen some students who have put tiny little thing there. It's wrong. It cannot go past that, because as soon as you get anything negative on the inside here, it becomes not a real number. From back in chapter 7, section 1, question 1. So be very careful about that. Do not go past that. A lot of students remember from chapter 3 that you make arrows at both ends and go slightly past the edges. So they try and figure out where they're going on this side. You don't go anywhere. It does not go there because those are not real numbers. So it cannot go past that solid dot there. It can only go continuing on this side. So be very careful when you're graphing it. What we're getting into here are called transformations in chapter, or actually in 121. So these are transformations. If you looked at this graph, it was the same graph as this, only instead of going this way, it was upside down. This one will have another change from the original graph. Here is, of course, our x and y t-table. If you are ever not sure, I strongly recommend that you just do every single x value from negative 6 to positive 6. Does that mean that I just asked you to plug in 13 numbers? Yes, I did. So we're going to plug in from negative 6, negative 5, negative 4, negative 3, negative 2, negative 1, 0, and then we'll keep going if we need to. And we're looking at the square root of negative 6 plus 5. That will simplify as the square root of negative 1. Even index negative in the right hand, you can't graph it. The square root of negative 5 plus 5 gives you the square root of 0. Hey, that's our good old friend 0. Negative 4 plus 5 gives us the square root of 1. Hey, we've done this before. These numbers here are from this t-table. So we might already know that these two aren't going to work. This is negative 3 and negative 2 with plus 5s. And that will give me a square root of 2, which we know does not come out nicely, and a square root of 3, which doesn't come out nicely. But hey, we should know that negative 1 plus 5 is going to be square root of 4, which will come out nicely. And you might think, hey, that's all we graphed in the past. So if we graph out negative 5, 0, and negative 4, 1, and negative 1, 2, but wait, look how much space there is on this side. There's another point there. Let's see if we can figure it out where it is without using the t-table. From back in chapter 3, we counted 1 squared is 1. We counted from the beginning spot, 1, 2. 2 squared is 4. 1, 2, 3, 4. Let's go back to the starting point here, and we're going to do 3 squared. 1, 2, 3. 3 squared is 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. We strongly suspect this point is going to come out right there. Let's test it. The x number is 4. So I'm going to skip down until I get to 4, and then I'll do 4 plus 5. Hey, that's the square root of 9, and the square root of 9 is 3. Let's see, is this at 4, 3? Yes, it is. But you can't just leave it hanging out there. We're going to have to take this graph and keep going, whee! Ta-da! Now, is this a straight line? It is not actually a straight line, but I have had some students, for something this large, they've used a straight edge just to make a really light line and then gone over it with hand. This is a non-linear graph. You're not supposed to be using a straight edge. So I've seen students go, and they're using straight lines. That's not correct. This is a parabola turned sideways called a square root function. So this should all be a smooth curve. There is a slight bobble in there because I did it by hand. So be careful. Now, you'll notice that I kept going up this way. This is good. I see a lot of students who do this. They go straight across. That's not correct. I've also seen some students who went, woo! And here, it just hit this one line. Well, 1 squared is 1, 2 squared is 4, 3 squared is 9, but is 4 squared equal to 10? No, it's not. This is hit too soon, I would have to take off points. So be very careful about that. You would want to know that the other point is out here, so it should be growing slightly. I've also had some people who have had that jump in. Also, again, remember, don't go past this original point. That point is a starting point, and it cannot go to the left, it cannot go below, because it only goes up and to the right. It's only half of the parabola. Continuing our transformations, before you learn transformations, again, you're going to be wanting to take a look at all of these. -6. If I had a negative in here, do you remember that it doesn't work? Because an even index and a negative number, all the negative x numbers are not going to work. So we're actually going to jump ahead. 0 will work. So the square root of 0 plus 3. Now be very careful here. What I see a lot of students do is they don't see that this vinculum here ends. So they draw it all the way over there. That is a totally different problem. It looks more like this one. So be careful. You have to pay attention to, does the vinculum go over the +5 or not? Because it will absolutely make a difference on how this moves. What we're going to find is that this one, if you think back to the last problem, moved it to the left 5. It says +5, but things that happen inside here with the x's, they lie. We've learned that from a long time ago. If I had something like x plus 5 and x minus 2 equaled 0, the answers were x equals -5 and +2. Those lie. Darn it. They have the right number but the wrong symbol. This said +5, but it really moved it to the left 5. This negative in the front flipped it upside down. We saw that back in chapter 3, where we had an x squared and a negative x squared. Now, we're going to have a square root of x graph. That is going to be a square root graph, and it's going to be moved to +3. Let's see what happens there. That is 0 plus 3, we get 3. Hey, we know that 1 works, and if you remember, then the next number that worked was 4, and the next number that worked was 9. 9 goes past the graph. Don't worry about it. All right, so over here we have square root of 1 plus 3. That's 1 plus 3, that is 4. And square root of 4 plus 3, that's 2 plus 3, that is 5. If we did this, square root of 9 plus 3, we would get 3 plus 3, which is 6. I want you to take a look at a pattern. 3, 4, 5, 6. Did you notice that we have the same pattern on all the previous problems? It didn't start off with 3. This started off with 3 with this one. The others start off with 0, 1, 2, 0, 1, 2, 0, 1, 2. There's a pattern like that. So if you ever see that your numbers are skipping a step, you missed somebody back there. So if we graph this, 0, 3, 1, 4, 4, 5, and if you wanted to estimate 9, 6, just to make sure you were aiming at the right spot, starting from here, do not go past it. Coming up this way, wow! Oh, I kind of missed it, but hey, it's off the graph, so yay. That is your square root graph. So a +3, this moves it up 3. This moved it left 5. This flipped it upside down, which will be called, in 121, a reflection across the x-axis. Ooh. We're starting to pre-teach you chapter 2 in 121. Chapter 7, Section 1, Question 5, Part 2 of 2. So, last time we were dealing with square root graphs. Now we are dealing with cube root graphs. Ew. So, a cube root, we have to find three numbers, all the same, that multiply to give you that number in the middle. Again, if you are ever not sure, you're going to plug in every single number. Oh my gosh, this graph has a lot more numbers than last time. Last time I asked you to plug in 13 numbers from -6 to +6. Now I have from -10 to +10. That's 21 numbers. Unless you can figure out how the patterns work, you have a lot of plugging in your future. So here we go. X and y, -10. The cube root of -10. Are there three numbers all the same that multiply to give you -10? 2 times 5 is 10, but there's not three numbers that are all the same. So we're not going to graph this. Is it part of our thing? Yes. It's not that we can't graph it, so we're not going to. So maybe we don't put a dash there. We're just not going to do it. All right, -9. Ooh, a lot of people think, hey, 3 times 3 is 9, but I need 3 of the same numbers, whoopsie, to make 9. And a lot of people think, ooh, 3 plus 3 plus 3. But that's adding. We need to have three numbers that multiply to give you this number. 9 breaks up as 3 times 3, that's only 2 of them. It would work on a square root, but not on a cube root. -8, the cube root of -8. Hey, that one actually works. Let's take a look. If I just looked at 8, 8 breaks up into 2 times 2 times 2. Notice how I did that. If you learn that 8 breaks up as 2 times 2 times 2, that is going to save you a massive amount of time in this chapter, and also in chapter 9. Now, to make it -8, all of them have to be negative. So this gives me -2. Hey, that's our first point. Woohoo! Yay! All right. -7. There are not three numbers all the same that give me -7 or -6 or -5 or -4 or -3 or, gosh, this is a lot of numbers that don't work. But do you remember on the last one where we had numbers in order? -2. The next number is going to be -1 times -1 times -1, which is, by their powers combined, -1. Oh, well, here look. It's going to be -1, which is going to be -1. Then the next one will be 0, 0, and 0, which will, by their powers combined, give you 0. Oh, neat. 0 will give you 0, and then 1, 1, and 1 will give you 1. And then 2, 2, and 2 will give you 8. Hey! On this side, these are the counting numbers, starting from -2 to +2. And look, there's a pattern. Kind of like when we were graphing out our parabolas. At -8, you get -2. At +8, you get +2. At -1, you get -1. At +1, you get +1. And in the middle of all of it is 0. That is not a -0. That's supposed to be kind of like an arrow showing you the cool patterns that we can get with math, because math is awesome. All right, so if we graph it, -8, -2, -1, -1. A lot of people only graph these 3 dots in the middle and they see a line. It's not a line, this is another nonlinear graph. And take a look, it has to come out here. So this side here, like a really stretched out parabola, but it's not a parabola, it is a cube root graph. Ooh, slightly going up. Take a look, it's above. It's slightly going up. And then this one, it goes down fast, and then it slows down. It hits here at -8, -2, and then slowly going down. This one has arrows at both ends. Now, why did the square root only have arrows at one end? And this has arrows at both ends. It goes back to chapter 7, section 1, section 1. Question 1. I can have positives or negatives when I have a cube root, because I can have 3 negatives that give me a negative. I can have 3 positives that give me a positive. That's why I can have a graph on both sides. But with a square root, if you have an even index number and you have a negative on the inside, that's not a real number, and we cannot yet graph those. Don't worry, that's coming up, not in this class. We will be able to graph imaginary and complex numbers later. More on that in Chapter 7, Section 7. For right now, not a real number means it's not going to get graphed. This is a graph of x cubed, or the cube root of x. So this is the cube root of x. Now, I want to look at this next graph. We already learned from last section, or last question, that the negative, all it does is it changes all those to the same thing, only negative. So if I take my negative 8, my negative 1, 0, 1, and 8, those are the 5 key points. Before it was negative 2, now it becomes positive 2. That was negative 1, now it becomes positive 1. That was 0, there's not a negative 0, so it's still 0, and negative 1, and negative 2. It changes the signs around. I'm using a different color because I want to show you what it's going to look like. So, negative 8, positive 2. Oh, they both have that 0, 0 point. But take a look, it's going to end up being the same graph, only backwards. So this is what I'm talking about when I say that later on in 121, you're going to have to graph these, and this is going to be called a vertical reflection across the x-axis. They just did a mirror image of what you had before, which is really cool. But wait, there's more. Let's take a look at, from our original graph, this one. We have the cube root of x plus 2. The x plus 2 is on the inside by the x's. And if you remember, it works backwards. It's going to make all your x's go that way 2 spaces. So if you wanted to copy it, 1, 2 to the left, 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 and 1, 2 to the left. That's how we could get those numbers. And what that's going to do is it's going to scooch all of these x's 1, 2 further to the left. So instead of negative 8, negative 1, 0, 1, and 8, we're going to use negative 10, negative 3, negative 2, negative 1, and 6. These are the numbers that are going to come out nicely. Now, for those of you who are like, this is confusing, I just want to plug in all 21 numbers, that is totally fine. Let's go over again how to plug this in. We have the cube root of negative 10 plus 2, which is the cube root of negative 8. That is why we have negative 10, negative 2. This point here that I did using transformations, which is a 121 concept, this plus 2 being in by the x lies to you. It says plus 2, which you would think means right 2, but because it's in by the left x, it means it goes left 2. Then we're going to plug in negative 3 plus 2, which gives us the cube root of negative 1, which is, let's see, which is negative 1. Oh, huh, that's negative 2. That's why it's strange. All right, here we go. Negative 2 plus 2 gives us the cube root of 0. And then the cube root of negative 1 plus 2 is the cube root of 1, which is 1, and the cube root of 6 plus 2. Hey, take a look. This 3 is getting ready to leap bodily out of my index number area. If it actually did, that would be horribly bad. So just to be careful, I'm going to make that a little bit longer so that stays as an index. Because if it ever pops out, then it suddenly becomes a square root and it's wrong. Here we get the cube root of 8. Ooh, let's keep that in there. And the cube root of 8 is 2. So this we have called a diving board because we want to make sure it stays there. That's how we get this graph. And again, from this point, we're going to go up and to the right, whee, through that point, and then very slowly, look, it's just barely above that line. And then down and to the left, whee, through that point. Oh, look at that, just barely above. Keep it careful. Make T-tables. T-tables are your friends. They are awesome. But wait, there's more. We can also have All right. So we were talking about this and transformations. The -4 will actually make it go down 4. So if I had everything go -4 in the y direction, each point would be moved down 4 spaces. Down 4 spaces, down 4 spaces, down 4 spaces. And I could actually draw my graph if I understood transformations, which is a 121 concept. We're not supposed to be there yet, but I want to introduce that to you because if you can do that, you can absolutely check your work so much faster. So we're going to think about the same old points that we were using because nothing happened to this x. So we can still use -8, -1, 0, 1, and 2. And plug it in. -8 cube root -4. Wow, this is taking me a while to write, so maybe we'll do it by the Henry Ford method of assembly line. We'll make a whole bunch of cube roots. That way all my cube roots come out correctly. Then we're going to plug in our numbers. And then we have to remember to put our -4s on there. Remembering that this vinculum cannot go over the -4, so make sure that there's a space there between the square root and the subtract 4. Otherwise it might come out to be something like this. So over here, the cube root of -8, you can have 3 negatives. So -2 minus 4 is -6. -1 minus 4 is -5. 0 minus 4 is -4. 1 minus 4 is -3. And, whoa, that was supposed to be not a 2, it was supposed to be an 8. Ah, there we go. And 2 minus 4 is -2. And that's how I was able to check -6, -5, -4, -3, -2. Ha-ha, if it didn't work, gosh, something went wrong. And I figured out very quickly, I had written the 2 instead of an 8 because I copied the y number instead of the x number. Tricky. These are the points. Let's double check. -8, -6, -1, -5, 0, -4, 1, -3, and 8, -2. That is a wonderful way of doing this. And then we graph, whee, and whee. Remember, slightly past the edges, arrows at both ends. So don't stop this like here. Some people stop there and go right there. Slightly past the edges, so keep going with that graph. Whee, slightly past the edges. Have that point there so that I can see where your points are, so that even if you were a little bit off with your whee graph, that I can still give you the points.